In this section, we'll look at coordinates and change of basis, or change of bases. And this gets into some funky stuff, but it's going to serve as a foundation for something that's coming up. I don't think in the next chapter. I think it's a chapter after that, or maybe even the one after that. The idea is, can we write things in terms of bases other than the standard basis? So suppose I gave you this vector, right? This nice, innocent-looking vector, 4, -2, 5. It was probably in the first chapter that we said we can write this as a linear combination of the SOBs, standard ordered bases. So I can write 4, -2, 5 as 4 times the vector 1, 0, 0, minus 2 times the vector 0, 1, 0, right? That's your J. And then plus 5 times the vector 0, 0, 1, that's your K. So that linear combination of the standard ordered bases will produce that vector X. You notice that the coefficients for -2 and 5 are the values that are in that vector X. All right. So suppose we have a non-standard basis, and we want to go back and forth between standard and non-standard bases. So here's the question. I want to find the coordinate matrix. And by the way, we can call this 4, -2, 5 as the coordinate matrix of X relative to the standard basis. Okay, so the coordinate matrix of X relative to the standard basis are these three coefficients, 4, -2, and 5. So now I'm going to flip things around a little bit. I'm going to say, given the coordinate matrix of X relative to a non-standard basis, for X relative to a non-standard basis, I want to go back to the standard basis. Right? So I want to go back to being able to write things in terms of 1, 0, 0, 0, 1, 0, etc. So here's the question. The coordinate matrix of X relative to my non-standard basis is -2, 3. And now I need to define the basis, because remember, the basis is not the standard basis anymore. So here my basis is -1, 4, 4, -1. Okay? And again, a reminder that this thing is a non-standard basis. Well, how do I do that? I'm looking for some coefficients. I would like to take -2 times the first element in the basis, which is -1, 4, and then plus 3 times the second elements in the basis, and see what I get. Well, that will give me a +2 plus 12 is 14, and then -8 minus 3 is -11. So the coordinates of X relative to the standard basis are 14 and -11. So multiplying -2 times the non-standard basis, right? So -2 times the non-standard basis plus 3 times the non-standard basis gives me 14, -11. That's the equivalent of multiplying 14 times the standard basis minus 11 times the standard basis. All right, so I'm going sort of back and forth. Let's talk about this in more general terms. Okay, in more general terms, I've got this basis, right? B is some basis, and it's got a bunch of vectors, v1, v2, all the way to vn. And specifically, that basis is a non-standard basis. It's an ordered basis, but it's not necessarily a standard basis. So this is a basis for some vector space V. And I'm going to let X be contained in that vector space, so that I can write X as C1, V1 plus C2, V2, all the way till I get to Cn, Vn. Where all these guys are now vectors, right? Vector 1, vector 2, vector 3, and I'm putting coefficients in front of the vectors. So these scalars are the coordinates of X relative to basis B. So the coordinates of X relative to that basis is the vector C1, C2, all the way till I get to C sub n. So those are the coefficients. All right, let's try an example for something relative to a non-standard basis and see how we do. So here's my question. Suppose I've got a non-standard basis. I'll call it B prime. Okay, that's my new basis. My new basis contains, so this is an example. My new basis contains two vectors, 2, -4, and 3, 8. And the vector in that vector space that I'm looking at is the vector 1, 1. So let's set up a linear combination. We know that that vector x that's in the vector space can be written as a linear combination of the vectors that are in that new basis. So C1, V1, C2, V2. All right. So that vector 1, 1 equals C1 times 2, -4 plus C2 times 3, 8. Set up a system from there. So 2 times C sub 1 plus 3 times C sub 2 is 1, and -4 times C sub 1 plus 8 times C sub 2 is equal to 1. All right, set this up in an augmented matrix. I end up with 2, 3, 1, -4, 8, 1. All right, you notice I could have taken the vectors in the basis and dropped them down the columns and then put the coordinates of the other vector on the other side. Can we row reduce this? Sure. Right? Shouldn't be too terrible. If I take twice the first row and add it to the second row, answer goes in the second row, I end up with what? +4, +6, +2. So my next row reduction becomes 2, 3, 1, 0, 14, 3. So from here, let's divide. Let's do some division to get these things down to ones in the pivot spots. So I get 1, 3/2, 1/2, 0, 1, 3/14. Ooh, some nice fractions here. All right, let's take linear combinations to get rid of that 3/2 that's up at the top. Yeah, there's going to be fractions involved. So let's do -3/2 row 2 plus row 1. Answer goes in row 1. So what numbers will that give me? That'll give me a 0, a -3/2. And if I multiply -3/2 times 3/14, that should give me a -9 over 28. All right, let's try this. In the top row, 1 plus the red 0 down the bottom is 1. 3/2 minus 3/2 is 0. If I take a half minus 9/28, well, a half is 14/28. So take 14/28 minus 9/28, and I get 5/28. Down the bottom, I get 0, 1, and 3/14. All right, so those numbers down the bottom on the right-hand side, that 5/8 and that 3/14, that's the coordinate matrix of x relative to B prime. So the coordinate matrix of x relative to that new basis is 5/28 and 3/14. Now, how do I know if I'm right? Well, let's try it out. Let's check. Take 5/28, and the first vector we were given in the basis was 2, -4. The second coefficient was 3/14 that we found, and the second vector was 3, 8. See if that really does equal the 1, 1. So this will give me a 10/28 plus 9/14. Well, 9/14 is the same as 18/28. So 18 plus 10, sure enough, that's 28/28, which is 1. Do it for the second one. -20/28. 24/14 is the same as 48/28. Add those together, and I really do get 1 again. All right, so it works out that if I multiply those coefficients that we found times the vectors in the basis, I really do get that vector that was on the other side, that vector we were calling x. All right, let's take another one and look at it a little bit differently. Same type of idea. Let's take B as a basis. Includes the vectors 1, 1 and 2, 1. And here, I'm going to give you the coordinate matrix for x relative to that basis. Okay, -3 and 5. And my question is, find the coordinate matrix of x relative to b prime. All right, what is b prime? I don't see a b prime up here. We're going to have to figure it out as we go along. So set up my linear combinations that I know. I know that there's some constant times the first basis vector plus some constant times the second basis vector equals -3, 5, which is the coordinate matrix of x relative to that basis that you were just given, so those are the two coefficients. I could have given you the vector, but why not give it to you that way? All right, let's set up our system of equations. We have C1 plus 2C2 is -3. We've got C1 plus C2 is 5. All right, so when I set up my matrix, I end up with 1, 2, 1, 1. Right, I dropped the columns down this way. Actually, I just read it right across. Times C1, C2 equals -3, 5. All right, so I just rewrote my system of equations with a matrix. Let's look at what I have here. Let's call this matrix P. This thing here is what we're trying to find. We're trying to find the coordinate matrix of x relative to b prime. On the other side, we were given the coordinate matrix for x relative to b. Now go back to those solving systems of equations and those matrix properties. What if I multiplied both sides of this matrix by P inverse? Okay, so if I multiply by P inverse, what will happen? On this left side, P inverse times P will just go away. Right? So I'll get this equals P inverse times the coordinate matrix of x relative to b. Well, P times P inverse is just the identity matrix, and the identity matrix times that coordinate matrix is just that coordinate matrix. So it turns out the coordinate matrix of x relative to b prime is just P inverse times the coordinate matrix of x relative to basis b. Great. So in theory, all I have to do is find the inverse of that coordinate matrix. Before I slide this up, let me write matrix P over here as 1, 2, 1, 1. Remember what the rules are for finding the inverse of a 2 by 2 matrix. First thing you need is you need the determinant. So the determinant of matrix P is going to be 1 minus 2, which is -1. Okay. Good news is the matrix has an inverse. And then what do? You switch the ones and the ones. Well, all right, this looks a little silly. So it'll be 1 over the determinant, so -1. Switch the ones and the ones, and then negate the other two. So -2, -1. Multiply that out, and P inverse will end up being -1, +2, +1, -1. What does this rule sitting up in the top corner over here say? It says if I take P inverse times the coordinate matrix of x relative to basis b, I'll end up with the answer that I want. So take -1, 2, 1, -1, and multiply it by that -3, 5 that we already have. What is this? This is P inverse times the coordinate matrix for x relative to b. And that will give me the coordinate matrix of x relative to b prime. So this gives me a 3 plus 10 is 13. Down the bottom, I get -3 minus 5, -8. This is the coordinate matrix of x relative to b prime. That's the answer I'm looking for. All right, try it out. See if it works. Take 13 times my first vector, which was 1, 1, minus 8 times the second vector, which is 2, 1, and see if I get -3, 5. So 13 minus 16 is -3. 13 minus 8 is 5. Sure enough, it checks out. It's the same as that vector over there. All right, so that's one way, and you notice I never actually found the other basis. Okay, how do I transition between these two? I kind of gave you a hint already. It's going to involve a transition matrix, and that transition matrix is the matrix that we call P. A couple of little rules that we're going to follow as we do this. The transition matrix. Suppose you have some original basis, which is B. So I'm using B as the original basis, and the new basis I'm going to call B prime. So the matrix P will transition you from B prime back to B, right? From the new basis back to the old basis. The inverse will transition you from B to B prime, from the old basis to the new basis. Now, how do you find those? Well, if you can set up matrices and row reduce, remember back when we were originally finding inverses? It's the same thing here. So suppose you've got two bases and you want to transition from B to B prime, then set it up to go from B to B prime. You're going to set up a augmented matrix that looks like this. The B prime goes first, the B goes second, and then you row reduce. You row reduce it until you get the identity matrix on one side, and what's on the other side will be P inverse, and that is the transition matrix. And the book has a whole set of theories and explanations with A sub n's and V sub n's and U sub n's, but this is the basic setup of it, and we will work at an example or two. All right, first thing is you want to know which direction you're going. So do you want to go from B prime to B, or do you want to go from B to B prime? That will tell you how to set up the matrix. The new matrix goes, the new basis goes first, the old basis goes second. So let's take a look at this. Let's find the transition matrix. From B to B prime, where matrix B is given as this. So we're operating at R3. I got negative 3, 0, negative 3. I've got negative 3, 2, negative 1. And I've got 1, 6, negative 1. All right, so there's my basis B. My basis B prime, my new basis, will be negative 6, negative 6, 0. Negative 2, negative 6, 4, and negative 2, negative 3, 7. All right, if we want to go from B to B prime, the first step is set up our augmented matrix. Okay, so our augmented matrix is going to have B prime on one side, B on the other side. How do these vectors go? They go down the columns. So my first column is going to be negative 6, negative 6, 0. Right? That's the first one here. The second one down the column will give me negative 2, negative 6, 4. Third one down the column will give me negative 2, negative 3, 7. So that's B prime. You don't have to draw that in there, but you can. Now I go down the columns for the original basis. Negative 3, 0, negative 3, negative 3, 2, negative 1, 1, 6, negative 1. All right, now row reduce. I set it up on a calculator to row reduce because not that it's not fun to row reduce this 3 by 6 matrix, but when I row reduced it, I came up with this. I ended up with an identity matrix on the left side and a matrix involving a whole bunch of fractions on the right-hand side. All right, so some of them are negative, some of them are positive. We have fourths and twelfths a lot. Third row is going to give us some thirds. All right, so now we have the identity matrix on this side and P inverse on that side. So what is my answer? The transition matrix is this. It's whatever's on the right-hand side. So yeah, I'm going to write it again because the question asks for what is a transition matrix, so I should write things out clearly. Here's -3/4, -17/12, -17/12, and the bottom row is 0, 2/3, 2/3. This thing here is the transition matrix. So take things from one basis to another, one basis multiplied by that transition matrix, and you'll get the coordinate matrices relative to the other basis. Try it. Grab your calculator and do B prime multiplied by P inverse, and you should get back the basis B. All right, let's try one other quick example, and then we'll be done with change of basis in this section. Then the next section, we'll look at applications. Suppose I've got this polynomial. I've got P of x equals 6x to the 4th minus 2x squared plus x minus 5. And I like the coordinate matrix of x relative to the standard basis for P4. Well, what's the standard basis for P4? Degrees of polynomials of degree 4 or less. That standard basis is going to be 1, x, x squared, x to the 3rd, x to the 4th, right? Those are the elements in my standard basis. So I can rewrite that polynomial as -5 times 1 plus 1 times x minus 2 times x squared. But you notice there's no x to the 3rd term. So I'm going to have to put a 0 times x to the 3rd and then plus 6 times x to the 4th. So the basis for, I'll call it P, relative to the standard basis is going to be -5, 1, -2, 0, 6. In that order because I'm going in the order of my basis. And I'm also going to include that 0 because there's no coefficient for the x to the 3rd. If I don't do that, I'm going to end up with my basis vector in a different space than the standard basis. All right? And that's it for this section.